In this video, I'm going to discuss intermolecular forces. Molecules interact with each other, and this is done through what's called intermolecular forces, or oftentimes abbreviated to IMFs. The intermolecular forces used depends on the polarity of the molecules that are interacting. The intermolecular forces are in order of decreasing strength, so the strongest one is called ion-dipole interactions. The next one is called hydrogen bonding interactions, so that's the second strongest one. The third strongest is the dipole-dipole interactions, and the weakest is the London dispersion forces. There are a couple more that don't get talked about very often that can fit between the dipole-dipole and the LDFs, but we're not really going to talk about those ones in this video. So if we look at each of these in turn, so ion-dipole interactions are the interaction between a polar molecule, which has a partial charge, and an ion, which has a full charge. So if we have water here and then a chloride ion, we have a partial positive on the hydrogen of the water and a full negative on the chloride ion. So we can have interactions between those. So that's just an electrostatic interaction. Or if we have a water molecule, then a positive ion such as sodium, the oxygen on water has a partial negative, and so it can interact electrostatically with the positive charge on the sodium. Hydrogen bonding is an interaction between a hydrogen that's bound to either an oxygen, a nitrogen, or a fluorine, and it's interacting with the oxygen, nitrogen, or fluorine on another molecule. So for instance, if we have two water molecules here, we have that the hydrogen on one is partial positive, and the oxygen on the other is partial negative, so we can have an electrostatic interaction between those. Or if we have two ammonia molecules, again, we have a partial positive on the hydrogen, partial negative on the nitrogen, and so we can have an electrostatic interaction there. We could also switch it up where we have the partial positive on a water interacting with the partial negative on the nitrogen of an ammonia, or the partial negative on the water oxygen interacting with the partial positive on the hydrogen of an ammonia. And then we can have something like this, where what we see is that we can have hydrogen bonding between the water here, which has the hydrogen bound to an oxygen, then the oxygen over here on the formaldehyde, which is not bound to a hydrogen. And so we would call that a hydrogen bond acceptor, because it can accept hydrogen bonds from something like water, where the water can act as a hydrogen bond donor, and as we saw earlier, it can also act as a hydrogen bond acceptor. So it has the oxygen, which can be the acceptor, and the hydrogen, which can be the donor. Then if we tried doing something like this, where you might think this looks like a hydrogen bond because we have the oxygen and the hydrogen interacting with each other, but this would not be considered a hydrogen bond because the hydrogen actually needs to be bound to an oxygen, a nitrogen, or a fluorine. So we would not call that a hydrogen bond. That might be the next one, which is called dipole-dipole interactions, but it is not a hydrogen bond because remember, the hydrogen has to be bound to an oxygen, a nitrogen, or a fluorine. And the reason for that is because the nitrogen, oxygen, and fluorine are our most electronegative atoms. And so when we have that larger difference in electronegativity between the hydrogen, what the hydrogen is bound to, that creates a stronger dipole. And so that makes it a stronger bond. So that's why we give it the special name hydrogen bonding, where hydrogen bonding is technically just a type of dipole-dipole interaction. It is a particularly strong one, so we give it a special name. So the dipole-dipole interactions then are essentially just any interactions between dipoles that does not involve hydrogen bonding. So like I said, hydrogen bonding just is a type of dipole-dipole interaction, but it's kind of a special strong one, and so we give it a special name. And so any other dipole-dipole interactions that's not a hydrogen bond, we just call those the dipole-dipole interactions. So that would be if we had something like this with the formaldehyde, where we have the partial negative on oxygen, partial positive on carbon, those interact, that gives us a dipole-dipole interaction. Or if we have the sulfur dioxide here, we have the partial negative on oxygen, partial positive on sulfur, and we can have that interaction there. So again, those are dipole-dipole interactions. They're the interactions of two polar molecules, but we call it dipole-dipole interactions. We're just excluding anything that we could call a hydrogen bond. Then the last one we're talking about are what are called the London dispersion forces, and these are often abbreviated as LDF. So these are weak interactions between two molecules caused by these transient dipoles that occur due to the movement of electrons within the molecule. In reality, the electrons are quantum mechanical, but for a survey class like this, we could think about just the fact that the electron is moving around between the two atoms in a bond, and it's going to spend more time next to ones that are more electronegative. But if we have a very small difference in the electronegativity, we have the electron moving around, but just because of sort of probabilistic things, the electron might end up spending a little bit more time around, say, the carbon instead of the hydrogen, which would create a transient, meaning very short-lived dipole at the hydrogen, and say on the other one we then have the hydrogen have a transient negative charge. And so when we have that go on, we have this very weak, very transient interaction, but these are happening probably hundreds, thousands, even million times a second. And so we can have these very weak, very transient interactions, but we see that if we have a lot of these going on, if we have these large chains, then these can actually start becoming quite strong. So with LDF, they are very weak by themselves, so a single LDF would be very weak, but when a lot of them are occurring at once, they can become quite strong. Thus, the longer a hydrocarbon chain becomes, the stronger the interactions between the molecules. So the analogy I always use is that it's kind of like Velcro. So if you have just two very small pieces of Velcro and put them together, it's going to be easy to take them apart. But if you have very large pieces of Velcro and put them together, it's going to be a lot harder to take apart. And so we can think of larger molecules as being the larger pieces of Velcro. And so if we want to think about some of the consequences of these intermolecular forces, we can think about solubility. And so the rule of thumb that you will often hear at this level of chemistry is that like dissolves like, and opposites do not dissolve each other. What we mean by that, for instance, is that polar molecules will dissolve other polar molecules. So, for example, water and methanol, which are both polar molecules, are mutually soluble. If you have a bunch of methanol and you put a little water in it, it will completely dissolve, and vice versa. If you have a bunch of water and put some methanol in it, it will completely dissolve. Then nonpolar molecules will dissolve nonpolar molecules. So for instance, hexane, which is a hydrocarbon, and octane, which is a hydrocarbon, are mutually soluble. You can dissolve as much of one into the other as you want. But then polar and nonpolar molecules will not dissolve each other. So water and hexane will not dissolve each other. Water being polar, hexane nonpolar, they do not dissolve each other. And this is because molecules must interact to dissolve each other, and if the molecules do not have similar IMFs, they will not interact very strongly, and therefore they will not dissolve each other. And these polarity considerations can also be used to look at things like melting point and boiling point. So for instance, water has a very high boiling point, even for such a small molecule. And that's because we have these strong hydrogen bonding interactions that hold the water molecules together. So for instance, something like H2S, which is going to have a very similar structure, and sulfur is in the same column as oxygen, so you'd expect it to be very similar, but because there is a much smaller difference in electronegativity between hydrogen and sulfur, the boiling point for H2S is negative 60 degrees Celsius, where for water it's 100 degrees Celsius. And so that's just because of the polarity of the water molecule. Similarly, the methane here, which is a very similar mass of a molecule, this has a boiling point of negative 162 degrees Celsius, where again, water is 100 degrees Celsius. And so we see that that polarity of the water molecule is doing a lot to actually increase the boiling point. And so long hydrocarbon chains with their many weak interactions can also add up to strong overall interactions. So having more carbons just means that there is a larger molecule and therefore more area for interactions. So for instance, the boiling point of butane, which only has 4 carbons, is negative 1 degree Celsius. The boiling point for pentane, which has 5 carbons, is 36 degrees Celsius. And the boiling point for hexane, which has 6 carbons, is 69 degrees Celsius. And you can actually find graphs that plot the boiling points for these hydrocarbons, and you see that as the number of carbons increases, the boiling point keeps increasing. But anyway, that was everything I wanted to talk about for this I hope you found that helpful, and I will see you in the next one.